Good morning to all of you. Uh, Before we proceed, I would kindly request you to change your name to registration number followed by your name. Could you please kindly change your name to registration number plus the followed by your name? Okay, thank you. We will start the lecture. Let me share my screen. Can you confirm whether the screen is visible and you can hear me clearly?
Yes, sir, we can hear you when it is visible.
Okay, thank you very much. And also in the chat, you can type your registration number for attendance purposes. Okay, let me start the session. There is a setting that I want to stop in the Zoom, but I cannot find it. Let me start the session anyway. So we are going to discuss the flexible AC transmission systems or FLEX devices under EE 674 modern power system course. Okay. So we will start with some kind of a background and why we need to look at this thing, uh, some kind of an introduction. Okay, we will start with some kind of a background and why we need. For that, I will need your input as well. Uh, Now, if we consider the power system consists of generation, and usually we step the generation voltage to a high voltage. Then we have the transmission network. We reduce the voltage to medium voltage level, and then at the near the load we will uh, reduce to the low voltage distribution value. So this is high voltage, we have medium voltage, and we have low voltage. So this can be like 33 kilovolt, this example, and this would be 400 volt. High voltage can be 132 kilovolt or 222 kilovolt. So this would be the voltage levels. Since we have the experience with the low voltage network, we will consider the low voltage network into the discussion. So we have the transformer and we will get the 400 volt. Next, we would have the feeder network. And then we connect loads to different points on the network. Now, can you raise your hand if your house is located near the transformer? When you raise your hand, if it is close to if your house is located near the transformer, okay, there is one person says that the home is located near the transformer, so you can lower your hand. And if somebody is there whose house is in the middle of the line, can you raise your hand? There are four people raise the hand. If your house is located at the end of the line, can you raise your hand? If your house is located at the end of the distribution line, can you raise your hand? I got responses from few students. I'm expecting the response from others as well. Okay, there are responses. Can you raise your hand if you have got electricity to your house? Raise your hand if you have got electricity connection at your home. Oh, very good response. Uh, we say that we have very high percentage of the electricity supply, but still we can see that when we consider our class, uh, there are, I think, about 20, more than 20 students, but still there are some significant number who doesn't have electricity. That's the conclusion that we can make. Okay, so now you can lower your hand. So when we consider the placement, so some of your homes are located near the transformer, whereas some are located at the end or in the middle. Now, what kind of issues that you have found when you get electricity? Especially the ones who are located towards the end of the distribution line, what kind of issues that you have experienced? Can
Higher
someone,
voltage drops.
who is this? I got the response, but who is this?
I am Dulaj.
Right, okay. So you have experienced high voltage drops. What else? Who else experienced high voltage drops? Nobody? Okay, Dulaj. So when did you experience the high voltage drops?
In the night time,
In the night time. Okay. So is there anybody who is working in power generation or electricity related company? Is there anybody who is working in power systems? I'm sorry, I'm expecting responses. Otherwise, this would be one-way communication and it is going to be difficult. So I expect responses from the students. Is there anybody working in power system industry? Okay, there is one. Can you raise your hand, everybody? Can everybody raise your hand in Zoom? Okay, thank you. There are students who are not raising hand. I assume that there's no need for you to just be in the class just because the lecture is going on, but I need the response from the students. Otherwise, I would say that next time the lecture will be conducted physically, and that would be the way. So I need the responses from the students. So you can lower your hand. Thank you. And I will ask the question again. Is there anybody who is working in power system industry? Okay, it seems that there's one person only working in. Okay, so now as consumers, you would experience high voltage drops at nights. There is one case. Uh, is that the only thing that you have experienced when you are working in the when at your home? How about the people who are residing near the transform? Have you experienced any issue? Can you raise if your home is located near the transformer? Can you raise again? Okay, Risha. So have you experienced any issue since you are residing closer to the transformer?
uh, suddenly breakdowns are affected highly.
It was not clear.
The suddenly breakdowns are affected highly.
Okay. I think probably you are not seeing the effect, but since your home is located closer to the transformer, you may experience higher voltages, even though the consumers towards the end of the distribution line experiences voltage drops in the night. The consumers in the closer to the transformer can experience higher voltages, especially in the light loaded conditions. So these are the possible problems that we can see in distribution lines. So we experience voltage variations throughout the line. Some consumers are experiencing lower voltage, whereas the other consumers experience higher voltages. So that's one of the problems that we see in the distribution network. You all can think about go back to maybe 10-15 years. When you think about 10-15 years back, I assume that you are in the school, but in a time that you can remember things and you have a visual memories clearly than the younger age, very young age. Now, can you think of the distribution network in your area maybe 15 years back? So 15 years back in your area, What can you say about the number of customers that has been connected to the distribution network? And when you come to today, what you can see. How many of you have experienced that the customer base has been grown over 15 years? If it is yes, can you raise your hand? Okay, thank you for the response. Thank you for the quick response. So what you have seen is that maybe at the beginning you may have very limited number of customers, but now by now you may have seen that large number of customers has been increasing the distribution network. Now, what is the problem of increase in the number of consumers in a distribution feeder? 2610, Ishan, what could be the problems when you see growth in the customer base?
Voltage drops in connections.
Voltage drops in the connection because you are seeing
Higher
customers, the power consumption increases, so voltage drops are going to increase. So in the first case that we considered, what we observed is that we have a network and we are seeing in partially, in sometimes we have the drops, voltage drops, but in some cases we can experience higher voltage. And in this case, we are thinking about down the line what would happen. So as the years goes by, we see an increase in the customer base. As a result, we are going to experience voltage issues in the network. Now, ideally, what should be the voltage allowed voltage limits in a distribution network? $25 to Abdullah. What is the allowed? Sorry.
Yes, sir. Can you repeat the question, please?
If you consider a distribution network, what is the allowed voltage variation? Plus or minus value percentage?
The plus or minus 5%.
Plus or minus 5%. Any other answers? 2531, I think Chandrasena.
6%, sir.
Plus or minus
6%.
6%.
Full voltage.
Okay. 26 Nirmal.
About 10%.
Plus or minus 10%. So we have three answers. So you can find out what is the correct value. Definitely it is not 5%. Either it is 6% or 10%. So you can search and see what is the value. So what we want to do is maintain the voltage levels of the distribution network within these allowed limits. Now this is for the distribution network. Similarly, these issues will be there in the high voltage network and medium voltage network. At a given time, there can be voltage drops. Voltage may drop below the allowed limit, or else it can increase above the allowed limit. Now, at the same time, if we consider the power system over the years, customer base will increase. When the customers are increasing, that means the load is going to increase. That will affect the distribution network. This doesn't only happen in one location of the distribution network, it will happen in many locations. As a result, that the power transfer capability requirement increase will be there for the medium voltage network as well as in the transmission networks. So therefore, we are going to see a problem in the network. So we need to have solutions for them. We need to have solutions. So we need to provide solutions for the voltage drops or over voltage conditions that we experience in certain periods of a day. And also we need to provide solutions for the gradual increase of the load in the network. Now, if we want to provide a solution for this case where the load increased during year by year, so what are the solutions that we can have? 2611 save mini. What we can do to support this kind of issue?
We can increase the transformer power.
So one is increase transformer rating. Is that what you're
Yes.
saying?
Yes.
So which means that replacing the transformer.
Yes.
Okay. Then 26-tree Mahela. Twenty-six-tree Mahela, what we can do? What is your solution?
Hello. Good
Yeah,
morning.
yeah,
Hello.
yeah.
Decrease the distance of the transformer.
What do you mean by reduce the distance of the transformer? What do you mean by that? It is not clear.
We can increase the number of transformers.
Okay, so that means are you suggesting to split this distribution line into segments and provide different power to different transformers? Is that what you're saying?
Yes.
Okay, so that means change the distribution line. Now, either
Excellent.
yeah, yes,
We can also change the tap position of the transformer, can we?
yeah, we can change the tap position. Thank you. But Chanaka, the change in the tap position, through that we can get to a limited results, isn't it? Because
Yes.
when you are trying to change the tap position, basically you are changing the voltage at the starting point of the distribution network. But that is limited because you have the loads connected to the line closer to the transformer. If you increase it, you can't increase beyond the rated allowed limit. So that is also going to be limited. So what you can see here is that we see some kind of issues in certain time of the day and sometimes some problems that we see over the years gradually creeping up. Now, if we consider this case, the second case where the number of consumers are increasing, now the solution can be to increase the transformer rating, but increasing the transformer rating only maybe not be a solution because we have the distribution line. So the cable rating may be limited. So even though we can change the transformer, we won't be able to increase because of the cable rating. So in that case, we may be need to increase the cable current rating, and we may need to replace the cable, as well as we maybe need to split the network, and we could introduce another transformer to power the number of consumers in the network. So basically what we are saying is that we will reduce the length of the distribution line. So these solutions are attractive, but we need to improve the infrastructure, which can lead to costly solution. So if we can provide solutions without changing the network configuration, without changing the infrastructure of the network, then it would be good. So these flexible AC transmission systems uses power electronics, and thereby it will help to overcome the issues that we are seeing in the network during certain period of the day, or a problem that has been accumulated over the years. So one solution is that flexible okay. So that's why we are learning this component, flexible AC transmission system. So you can see why we need this, because we are experiencing voltage drop, so high voltage during certain period of the time in a network, or else we are seeing that the customer base is increasing. As a result, with the system that we have, we won't be able to support other than creating another path or the path to support the increase in loads. So here what we are trying to do is, without changing the network configuration, how we can use power electronics to support these issues. So I assume that it is clear why we are learning that one. So first we will look at some basics related to power transfer capability, and then we will see what are the options that we have, and through that options how we can increase the power transfer capability in a transmission or distribution line. And after that we will be discussing about the real arrangements that we use, real arrangement or real converters that we use to support these issues. So let's go to the power transfer capability analysis. So we will consider a line we have a sending end. In between, we have a line. I will represent the line with the reactance with the X. We will have a sending end voltage Vs, and we have the receiving end voltage Vr. And also we have the current flowing through the network. I will take as I. So we will consider this simple network. And for the simplicity, I will assume that the receiving end voltage is equals to V and angle 0. And I will assume that the receiving end, sending end voltage magnitude is same as the receiving end voltage magnitude, and the angle is equals to delta. Now, if this is the case, can you find out what would be the power transfer capability, active power, reactive power, and apparent power through the line? Can you quickly work out what would be the apparent, active, and reactive power? Can you quickly work out? Okay, so we can write equation for the current. So I will be equals to Vs minus Vr over Jx, which we can write as V delta minus V0 over Jx. So we have the current. Then we can consider the power is equals to Vi conjugate. So from that we can write the voltage if we consider the sending end. Okay, we consider the receiving end. So we have VR I conjugate. So VR is V angle 0 and current is V delta minus V0 over Jx and conjugate. So this we can write as V0 V over X delta minus 90 V over X minus 90 and conjugate. So we have V0 V over X 90 minus delta V over X 90. So this we would get as V squared over X angle 90 minus delta V squared over X angle 90. So this is what we are going to get as the apparent power. Now using this we can find out what would be the active power at the receiving end. So we get V squared over S cos 90 minus delta V squared over X cos delta. I think I made a mistake. Let's see. So this is QR and PR is going to be V squared over X sine 90 minus delta V squared over X. Okay. Sine 90 V squared over X sine delta minus 0 we would get V squared over X cos delta minus 1. So here we get the active and reactive power at the receiving end. So similarly, you would be able to get the active and reactive power at the receiving end. Can I go to the next page? So when we consider the sending end, earlier I consider the receiving end. If we consider the sending end power, we would have Vs times I conjugate. So Vs is V delta. I would be Vx V over X delta minus 90 V over X minus 90 conjugate. So this we can write V delta V over X 90 minus delta, and we have V over X 90. So this is we are going to get as V squared over X 90 minus V squared over X 90 plus delta. So we can get PR, PS and QS. So PS we are going to get as V squared over X 1 minus cos delta. Qx we are going to get as V squared over X. So these are the sending in and receiving end powers that we are going to get when we consider a transmission line. So can you plot what would be the active power in the receiving end against the angle? Uh, 2610, Ishan, can you show your PR versus delta curve? Twenty-six ten, Ishan, can you show your curve?
So I understand how is
We have to move quickly. 2530, Chanak, can you show your one?
So I'm also still figuring out 1 minus cos part. So after I will show you.
So can you raise your hand if you have followed the derivation up to now? Can you raise your hand if you have followed the derivation up to now? Okay. Okay, so you are following the lecture. So 13 has raised the hand. Now, what do you think? Is this derivation correct or incorrect? Okay, you can lower your hand. Raise your hand if you think the derivation is correct. Raise your hand if you think the derivation is correct. Raise your hand if the derivation is incorrect. If you think the derivation is incorrect, can you raise your hand? Okay, 25-6, what's your name? What is your name? Hello? Edri Singh. So what is the problem here?
There is a problem is a P and Q is P is actually V squared divided by sine delta.
Uh-huh.
Final one, sir.
This one.
P and Q is interchange.
Uh-huh. How about this one? Is this correct?
Yeah.
This is correct.
Yes, sir.
So how many of you think this is correct? Can you raise your hand? How many of you think this is incorrect? Chanaka, you have raised. Chanaka, is this correct or incorrect?
So we QR reactive power v squared over x sine 90 minus delta. So the final answer would be v squared x cos delta. And likewise, in the PR also we are v squared over x cos 90 minus delta. Then v squared x sine, yeah, like that.
So I will make mistakes deliberately in this session. So you need to pick up if I make a mistake. Okay, so this is incorrect. So these two should be interchanged. So this is the active power and this is the reactive power. And similarly, this should be interchanged in the receiving sending end. So this is the reactive power and this is the active power at the sending end. So what we are going to see is that we would see a sinusoidal variation when we change with angle delta. So at angle 90, we would see the highest power transfer in the line, and that would be equals to V squared over X. So which means that when we want to transfer the power through the line, we need to change the angle so that we can send the desired power through the line. Now, if we want to increase the power transfer capability, so according to this equation, we cannot change much on the voltage. So what we have is we can change the reactance, so we can change the angle. So basically, the reactance will determined by the line, and so what we have is angle. So delta can be changed accordingly. So this is what happens if we consider a normal line where we have the sending and the receiving end. So our power transfer capability is limited to this arrangement. So now what we can as a solution for the problems that we have faced discussed earlier, we need to provide solutions. So we have two solutions to improve the power transfer capability in a line. So one option is to use the shunt compensation. Second option is to use series compensation. So we will discuss these two methods, how the shunt compensation or series compensation help to increase the power transfer capability. So if that is the case, we should see increase in the sending end power or the receiving end power value through the shunt or the series compensation. Or then, so we will look at the theory behind that, and after that we will see how we can practically implement these shunt and series compensators. So that's our goal in this course. So we will focus on the shunt compensation now. So in the shunt compensation, what we are going to do is we would have the sending end, and then we have the receiving end. And what we are going to do is we are going to split the line into two, and we are going to place reactive power supply compensator to the line. So for the simplicity, I will assume that this is divided into equal halves. So this is going to be an ideal compensator. So therefore, the compensator active power is going to be 0. So there would be a certain amount of power provided by the sending end, and there would be certain amount of power received at the receiving end. So this is going to be a lossless system. So if we so we will assume that PR is equals to PS. So we are placing this one and we are going to improve the power transfer capability. So can you find out when we consider the sending end, what would be the apparent power, sending end active power, and the sending end reactive power. So in this, the way that we have selected the location of the compensator, I will assume that Vs is going to be equals to V angle delta. C I will assume as angle magnitude V angle delta by 2, and the receiving end I will assume as V angle 0. So this is my assumption. So can you find out what would be the sending end active and reactive power, receiving end active and reactive power, and also the power delivered by the compensator. So can you quickly work out that? I'll give 10 minutes for you to derive the values, equations.
So what is a compensator? Excuse me, sir.
So when you solve, you would get this equation for the sending end power that would be equals to 2v squared over x sine delta by 2. And then for the reactive power, we get 2v squared over x 1 minus cos delta by 2. So that would be the sending end active and reactive power. In the same way, you should be able to prove the receiving end active and reactive powers. So for that, we have to consider the midpoint to the receiving end voltage. So that would be V delta by 2 minus V0 over Jx. And you can prove that the receiving end active power would be equals to 2v squared over x sine delta by 2, and the reactive power would be equals to 2v squared over x, you get cos delta by 2 minus 1. So that would be the answer that you would get for the receiving end active and reactive powers. So then we can plot the active power variations against delta. If we consider the system without the compensator, what we observed is that with the delta, so at 5 by 2, we had the highest power transfer, so that would be equals to v squared over x. But in this case, with the shunt compensator, now we get twice the that value. So the maximum power in case of the shunt compensator would be 2v squared over x. So we are increasing the power, but there is another point is that angle is now sine delta by 2. So the peak will happen when the angle is equals to 180. So for this one, what you are going to see is that you will see it's not a linear one. So we are going to see that this is this would be our curve. So what we are going to see is that angle phi, we would see the maximum power transfer capability, and that would be equals to 2v squared over x. So by implementing the shunt compensator, this compensator, we have doubled the power transfer capability in the line. So that is an advantage when it comes to the shunt compensator. Now we can extend the analysis and we can find out how much power would be provided by the compensator. So if I assume that the compensator current is going to be flowing into the circuit by compensator, so we can write that I Sm plus okay, I will it in the other way around. Is providing current. So if that is the case, we can write the compensator is going to be equals to I middle point to the receiving end. So since we know these two values, we can find out what would be the compensator current. And so once we know the compensator current, we can find out what would be the compensator power consumption. So we have the S compensator. So that would be equals to middle voltage times the compensator current conjugate. and this is going to be equals to 4v squared over x angle 90 minus 2v squared over x angle 90 plus delta by 2 minus 2v squared over x angle 90 minus delta by 2. So this is what we are going to get. And if you do the simplifications on this one, you would see that the compensator active power is going to be 0, but the reactive power is not 0. The compensator reactive power would be equals to 4v squared over x 1 minus cos delta by 2. So that would be the reactive power. So which means that even though we can double the power transfer capability in the line, that would come in the expense of a compensator where it can provide the reactive power given by this equation 4v squared over x 1 minus cos delta by 2. So that amount of power, reactive power, should be provided by the compensator. So the compensator will be placed in the middle middle point of the one. So through the shunt compensator, we would be able to regulate the voltage under the heavy loading condition and also light loading conditions. So in the light loading condition, voltage is going to increase. In the heavy loading condition, the voltage is going to be reduced. So in both cases, this compensator can support. So what I have done here is for a special case where the compensator is placed at the middle of the line, but in all the cases we will be not able to place the compensator on the middle of the line. So depending on the in real situation, that place may be not accessible, so we will not be able to place it in the middle. In that case, we maybe need to place that in a different length. So that is going to have an impact on the power transfer capability. So this equation only valids when the compensator is placed in the middle. So if you place the compensator at a here in equal distance, but if you place it in a not at an equal distance, then the impedance that we are seeing on segments are going to be different, and that will have an impact on the power transfer capability. So in such situations, you need to find out which segment is going to dominate, whether it is the small segment or the large segment. So you need to do the analysis in that case, and you need to find out what would be the possible power transfer capability improvement. So I will give I will provide some examples. I will do an example, and I will ask you to work out a few cases of the shunt compensation placed at different places. For that one, you can work out what will be the answers. So this is the first one. I think there was one person raised the hand. Who was that? Yeah, Dhananjay. What was your question?
Sir, can we consider the compensator as a capacitor bank?
Well, it depends on the requirement that we need. In certain case, that's why I mentioned that this can be used to in a place where we would have the under voltage issues, and also we can use this in a over voltage situation. So Over voltage means the light loading condition, under voltage means the heavy loading condition. So depending on the problem that we have to select what kind of a compensator we need. So in some places it can be the capacitor, some cases it can be the inductor. Did my answer clarify your doubt, Dhananjay?
Yes, sir. Thank you.
Okay. So that is the shunt compensation. So now we will look at the second one, which is the series compensators. So in the shunt compensator, the compensator was connected shunt way, but in the series compensator, it will be placed in series with the line. So this is the sending end Vs, and we have the receiving end Vr. So here I'm again assuming that this is split into two halves, and we have the compensator here. This is the sending end, and this is the receiving end. So now the current would be Vs minus Vr minus Vc divided by Jx. So based on the voltage that we are going to introduce, the current flowing can be controlled. Thereby, we can control the power transfer capability. So basically, again, this series compensator is not going to provide active power to the network. Therefore, it only support in providing reactive power or absorbing reactive power. So if it is not providing active or reactive power, we can represent this compensator with a variable in reactance term. We have we sending and we receiving. So I mark as Jx by 2. and we have the compensator. So if that is the case, we can write the current as, now we have Vs minus Vr. Now what we have is the X minus Xc. So where Xc is the compensated reactance. So now this X can be positive or negative. So if Xc is positive, that means we are adding an inductive reactance term. If it is negative, we are going to introduce capacitive reactance. If it is positive, it is going to be capacitive because we have the negative term here. If it is negative, then we are going to have the reactive element. So, or the inductive. If it is positive, we are introducing a capacitor in the line. So if we have a capacitance, what would happen is we are going to effectively reduce the inductive reactance in the transmission line. If we place an inductor, we are increasing the inductive reactance. So that means this value is going to increase. So we can see that we are going to keep the voltages as it is, but we are going to change the effective line impedance of the line. Now the equivalent, so we can write this the compensator value as a fraction of the reactance of the line. So if we represent in this way, the equivalent reactance of the network can be written as X minus R times X. So we have 1 minus R times X. So by varying R, we can vary the effective X value that we are going to utilize. So once we have that, we should be able to find out what would be the active, reactive, and apparent power. So I will give you 5 minutes or 5 to 10 minutes to work out what would be the active, reactive, and apparent power when we have a series compensation. So when you do the simplification, you would get this equation. So what you are going to get is that you can write the current as V delta minus V0 over J x1 minus r. So the active apparent power would be V squared over x1 minus r angle 90 minus V squared over x1 minus r angle 90 plus delta. So from this one, we can expand the active and reactive powers. So this is the active power and this is the reactive power that we are going to get. So if we plot the curves, if you look at the equation, delta is angle is delta, so it is not going to change. So the peak will happen at 5/2 and again it will be 0 at angle 5. So the curve would be something like this. But as we change our R value, the amount of power that will be transmitted is going to change. So as R increases, 1 minus R is going to be decreased as the active. As a result, the power is going to increase. As we increase the R value, what we are going to see is the active power, peak active power is going to increase. So that's the advantage with the series compensation. Without change in the angle, we are going to increase the peak power transfer. Of course, if your R is negative value, then this value is going to increase so that your power transfer capability is actually going to decrease. So that means if you place inductive element as the compensator, then effective inductance element as the compensator, then this value is going to be greater than the normal value, and then you would see the V squared over X term is going to reduce. So this is how the series compensator works. So again, you can consider the compensator power SC. For that, we need to consider the voltage drop across the compensator and current conjugate. So this compensator we can write as the impedance times the current times current conjugate. So from that one, you should be able to get the equation for the compensator. So this you would get as X compensator divided by X squared 1 minus R squared, and you would get 2V squared angle 90 minus V squared angle 90 plus delta, and you'd get V squared angle 90 minus delta. So from this one, you should be able to get the compensator active power. And when you solve it, you would get that as 0. And the compensator reactive power will be given by 2V squared R over X times 1 minus R squared 1 minus cos delta. So using this method, you should be able to calculate the reactive power provided by the compensator. Okay, so this is the shunt series compensation. So what we looked at was the shunt and series compensation, how we can, what is theory behind that. But here what we are going to do is we are going to effectively change the compensator reactance. So depending on the loading condition, we should be able to change this R value dynamically so that we maintain, regulate the voltage within the limits. So that means we should be able to measure the status of the distribution network, and accordingly we should be able to change the inductance or the capacitor. So we need to change the inductance, or we need to change the capacitance, and also we need to switch between inductance and capacitance. So how we are going to do that? Are we going to use variable inductors? If that is the case, how we are going to control the variable inductor? Are we going to use the variable capacitors? And if so, how we are going to do? Can we do that? Or else do we have a alternative method for that? So that the same thing, same questions will be there when we consider the shunt compensation as well. So how we are going to realize the shunt compensation? Are we going to use a fixed capacitor? So if you use a fixed capacitor, what is the problem? How we are going to vary the reactive power provided by the capacitor. So those are the practical problems that we have when we are trying to implement the series or the shunt compensation. So we will take a 15 minutes break, and once the break, 15 to 20 minutes break. So once we complete that break, we will look at how we can practically implement or realize these shunt and series compensation. Okay, so we will take a break, and we will start again after the break. Okay, it starts the session again after the break. To check whether you are back with the session, can you raise your hand if you are back? Okay, thank you. You can lower your hands and now using different capacitors or different inductors, variable inductors, variable capacitors kind of thing is going to be difficult uh, because we need to control them and implementing that kind of variable inductors or capacitors for the requirement of a power system. It is going to be a difficult thing. So what we are going to do is we are going to use power electronic converters uh, to mimic the effect of variable inductors or variable capacitors so that we can provide varying reactive power to the system so that we can regulate the power flow in the network or improve the power flow in the network. Now, when it comes to the power electronic converters, we can use, so now I'm going to do some little bit of review on power electronics and some of the devices that we can use them and look at some circuits related which are frequently used in the with the FEX devices. So okay, so okay, so can you name some of the power semiconductor devices that we are using in power electronic converters?
IGBT,
Okay.
Thyristors.
Thank you. Any other answers?
MOSFET,
MOSFETs. What else?
Thyristors.
Thank you. I have noted thyristors earlier.
Power diodes.
Diodes. Any other possible devices? Okay, thank you for the response. So these are the commonly used. Did somebody try to answer? Okay, so diodes, and one possible option is the power BJTs, but if we consider the practical applications today, power BJTs are not used much, but the other devices are used in the power electronic converters. Now, out of these, if we forget about BJTs, out of these devices, for the implementation of FACS devices, we rely on these thyristors a lot. Thyristors are used in FACS devices a lot. That doesn't say that the IGBTs or MOSFETs are not used in FACS devices. They are used, but if you look at the most of the FACS devices that we will discuss in the next uh, few hours of this section, most of the converters that we are going to discuss will be using thyristors. And of course we will use the MOSFET, IGBT, and diode used converters as well. But this would be thyristor-based converters are going to be used a lot in the FACS devices arrangement. Therefore, we will make a brief review on the thyristors and thyristor circuits so that you will be in a good positions to understand how these circuits are going to work. So can you raise your hand if you have learned about thyristors in your undergraduate program? The thyristor, the symbol, characteristic curve, VI characteristic curve, and then thyristor-based power electronic converters. If you have learned in your undergraduate program, can you raise your hand? Okay, thank you. So, how many of you can remember the fundamentals behind thyristors? If you can remember the fundamentals, the characteristic curve, etc., can you raise your hand? Okay, there is not many who can remember. So we will do a basic review. So thyristor is kind of an extension of a diode. So if we take the thyristor circuit, it's like this. You have the anode and cathode, you have a gate. So the gate will enable us to control the current flow of the thyristor. So if I mark the voltage drop across the thyristor as VT and current as IT, so we can identify three operating regions for a thyristor. You have the reverse bias mode, then you have the second mode, forward blocking mode, and then you have the forward on mode. In the forward blocking and forward on mode, the device will be forward biased. Now, when we consider the diode has two modes. It does not have the forward blocking mode. But with the thyristor, we have the forward blocking mode. So when we want to turn on the device, it should be in the forward bias condition. and the signal should be provided to the gate, then only the device will be moved into the on state. So if we consider the equivalent, the characteristic curve of a thyristor, you have Vt and It. We consider an ideal thyristor. Ideal thyristor will block the reverse current flow. So you would see you can apply any voltage in the reverse bias condition, but the current will be zero. So this is the reverse bias condition. Then you can have make sure you can apply any amount of positive voltage, but the current will be zero. So this would be the forward blocking mode. And also you can be in the on state where you can send any amount of current while the device is turned on. So this is the forward on state, and this is the forward blocking mode. So, but when it comes to the practical thyristors, we don't see this. In the practical circuits, there would be a small leakage current flowing, and afterwards it is going to break down. So this would be the reverse biased characteristic of a thyristor. So you have the breakdown voltage VBR. So after certain voltage, the device will fail. Then when it comes to the forward blocking condition, what would happen is that there would be a small leakage current flowing through the device up to some extent, so up to certain voltage, so VBO. So till that voltage, the device can block the voltage. Current flow will be limited to this leakage current. But after, if we apply a voltage beyond this breakdown voltage, then the device will be moved into the on state. So in the on state, what you are going to see is that you are going to see this kind of characteristics. So the current will be increased and the voltage drop because the device is going to, yeah. So this is after the breakdown. Till the breakdown happens, the device can withstand the current flow. So here Ig is 0. So the gate current is going to be 0. But if we consider the on state, what would happen is that on the on state, after a certain voltage, if we give a current flow, then it is going to follow this curve. So this is for Ig greater than 0. So we are going to, when it is in the forward blocking mode, we are going to give a current signal pulse to the gate. So that will trigger this device to be moving into the on state, and it will be following this characteristic curve. So this is forward on mode, and this is forward blocking mode. So we have the forward blocking mode and forward on mode. So that is the advantage of the thyristor. So it's similar to the diode, but additionally we have the forward blocking mode, so we can control the current flow. But once the device in the forward blocking mode, if we give get current pulse, then it is going into the forward on mode. But once it moved into the on state, turning off the device, we cannot control. It will conduct until the current becomes zero. So it's similar to the diode. With the diode also, when it is in the forward bias condition, until the current becomes zero, even though the voltage is negative, the device will conduct. So that will be there for the thyristor as well. So until the current becomes zero, the device will be in the conduction mode. So, but there are some variants of thyristors where you can control where it is turned off, but in that one you cannot control where it is being turned on. So this is the thyristor. So we can have thyristor based circuits, and from that we can control the voltage or the current flowing through the circuit. So that we will discuss an example of the benefit of thyristor circuits. Now if you consider you have a sinusoidal supply, and if you have a diode connected to a resistive load, you should be able to get the output voltage and output current. So we will assume that Vs is equals to Vm sine omega t. So you can plot the waveforms. So we have Vs. So Vs is going to be omega t. So what would be V out and I out for this case? Can you draw the V out and I out? And then we will consider the circuit with the thyristor. So can someone show the voltage and current waveform for the diode circuit? Can a volunteer show me the waveforms for the diode circuit? (26.5) Chamidu Gunaratna, can you show your waveform?
So I'm still drawing. It's like the upper part coming with the drop 0.7 drop like that.
Can you quickly show it? Because this is a circuit that you learn in A levels as well as undergraduate program, so it shouldn't take much time to draw the waveform. Fernando 26.4, can you show the waveform?
We draw it as the positive phase.
Can you show it?
So I draw it in the book. So
Can you show it through video? Chanaka, I can't see it because it's not focusing. It's not focused. There is a focusing issue. Can you show it now, Chanaka? I can't see. I just see a. Are you using the blurring in your thing? Are you with the zoom? Are you blurring your image?
No, sir. So shall I just say it then? The first waveform, the first 0 to 5 waveform, half the sinusoidal is present
Yeah.
in the diode. The second part, 5 to 2, 5 is absent, the 0 line. And the third 2, 5 to 3, 5 over 2 part is also present.
Okay. So if we take the voltage waveform, is it like this, Chanaka?
Yes, sir.
So your current waveform would be,
Yeah,
you would have the
the
same
shape will be
shape,
same.
but the peak will be different based on
Different.
the resistance value. So this is what we are going to see with the diode circuit. So the magnitude will depend on the supply voltage. But here with the thyristor, now what would happen is that we will be providing a gate signal to the system. So when there is a positive voltage, it will wait till the firing signal or the gate signal is provided. So if I assume that I'm going to provide the gate signal at angle alpha, till then the voltage is going to be 0. So you have a 0 voltage until that firing signal comes. So once the firing signal comes, this is going to move on to the forward on state. So that means it is going to conduct. So it is going to behave like this. And if we consider the current waveform, it would be the same, it would have a similar shape. So it is going to, depending on the resistance, current will be different. So you are going to see this kind of a current waveform. And at angle phi, the voltage will be 0 and the current will be 0. So then the device will move on to the reverse bias condition. So your output voltage would be 0 during that period. So what you can see when you compare these two with the resistive load, in the negative half, the voltage and current are 0, so there is no difference. But if we consider the voltage, output voltage in this condition is different from here. So if we find out the average voltage, we out average for the circuit here. What you have is 1 over 2 phi 0 to phi Vm sine omega t dt. So this would be equals to 1 over 2 phi Vm over tau phi. So we have cos omega t we will integrate omega t. So 0 to phi. So we have Vm over 2 phi. Cos 0 is 1. Cos phi is minus 1. So we have 1. So we have Vm over 5. This is for using a diode.
Excuse me.
Yeah.
So for the for the thyristor, what happens if we have multiple firing signals in the gate? In the illustration, you have mentioned that in an alpha distance, there is a firing sequence. From that point onward, it starts to allow the voltage to flow.
Yeah.
But what happens if another firing sequence happens? Because I did not correctly get the
So
operation
we
of the
at what interval are you going to give the next firing?
some interval greater than the alpha, but not in the negative part, within the positive angle.
Alpha to 5.
Yeah, within that range.
Within the alpha to 5, there is no point of giving the firing signal again, because the thing is, it is in the forward bias. Now it is in the on state. So once it is moved to the on state, it will be in the on state until the current becomes 0. So why we are providing this pulse is to move the thyristor from forward blocking to on state. So once it is reached the on state, there is no point of giving the signal again. You don't need to provide this signal continuously, either continuously, or you don't need to provide the signal again to the circuit. There is no use of that.
So
Once-
there is no way to get the thyristor get from a forward conducting state to forward blocking state, no?
No, we can't get it. It will conduct until it is been current is 0.
Okay.
Thank you. This is for the diode circuit. So if we consider the thyristor circuit, we can consider the V out average. So that would be 1 over 2 phi. Now what we have is alpha to phi Vm sine omega t d omega t So this is going to be Vm over 2 phi. So we have plus omega t, and we have alpha to phi. So this is going to be Vm over 2 phi cos alpha plus 1. So now you can see the average output voltage is not different at the load. Earlier we had Vm over 5, but now we have Vm over 2 phi. Of course, when alpha goes to 5, you would get the same answer. Now, if you go for alpha equal to 0, you would get the same answer as this one. If you increase alpha, then what would happen is the average voltage is going to be less than that. So that is with the resistive load for the thyristor circuit. But in the circuits that we are going to use with the thyristor, the compensators, we will be using inductors and capacitors. So therefore, we need to have different the signals providing places should be different. So now for this one, when the signal is provided, the current is positive. But we have to remember, if we have let's consider a circuit like this. We consider the reactance XO, inductance L. So for this one, what we are going to see is Vs and omega t. So if we have Vs like this, then Is is going to be lagging by 90 degrees. So which means that when we are having a positive voltage, the current is going to be negative. So there will be negative current flow when the voltage is positive. So if we are trying to control this using a thyristor, then we are going to have problems. So let's say now, if we want to implement this with a diode circuit, let's say we have between bit, we can have it using a back-to-back thyristors, isn't it? So if we include a back-to-back thyristor, then when it is positive, voltage is positive, it is going to conduct in this direction, and when the voltage is negative, even with this, we have the same issue. Anyway, what I wanted to tell is that now, if we are, let's say we are trying to implement this with a thyristor. Let's say we have two thyristors. One is in this direction, other is in this direction. So if that is the case, then okay, okay, we will consider the circuit, not this circuit. I will this in the next page. So we'll keep this one. So when you can see that when in the angle 90, when the voltage is positive, current is negative. Now in this side, 90 to 180, you have positive voltage and positive current. When you go from 5 to 35 by 2, your voltage is negative, current is positive, then 35 by 2 to 25, voltage is negative and current is negative. So now if you have a circuit like this, you have a resistor here. So now in this case, our output voltage is going to be same as the input voltage, and the current is going to be same as this is IS, I out, and this is going V out. Sorry, this is VS. Yeah, we are going to have the same circuit. So we are going to have this is V out, and this is going to be our I out. If you have a thyristor circuit, let's say we are going to apply pulses in this place. For this is for, if I mark, this is T1 and this is T2. So this is T1 firing signal, this is T2 firing signals. Then what we are going to see is output voltage like this. Then this would be our output voltage, and our output current waveform would be in the same shape. But instead of a resistive load, now if we connect an inductive load, then we are going to have a problem, because when the voltage is positive, this thyristor will be conducting. At the same time, the current should be negative. So that is not possible to realize in the circuit. So if we try to provide the firing signal at this location, we won't be able to do it. So if you have a circuit like this, this kind of a circuit, VS, L, or X value. So then we are going to have this kind of waveform. So we cannot give a firing signal in this region, because when the voltage is positive, current is going to be negative. So we can only give a signal, firing signal after 90 degrees, because after 90 degrees, voltage is positive and the current is positive. So then we are going into the positive, the device will be in the forward on state. So once that is happened, until the current becomes zero, even the voltage is negative, the device will conduct. So again, when we consider after this point, voltage is negative and current is negative, so we can give the firing signal to the other circuit. So with the inductive or capacitive circuits, firing angle would be greater than 5 by 2. That is because the voltage and currents are going to be shifted by 90 degrees. Is it clear? So I discussed briefly on the thyristors with the resistive loads and briefly in the inductive load. So is it clear for all of you, or is there unclear point?
Clear, sir.
Okay, thank you. So with that, we can move on to the fax devices. So you have the basic understanding of the thyristor and thyristor circuits. So let's look at how we can realize the fax devices. So first I will discuss about the fax devices that we can use with the shunt compensation, and then we will discuss the fax devices that we can use with the series compensation. So these are possible fax devices that we can use with the shunt compensation. So we will discuss them in detail next. So first we will discuss about the thyristor control reactor. So you have a reactor X. So I will take as L. So I say cell. L is the value, so we can write XL is equals to omega L. So we have T1, T2 thyristors, and this is the supply voltage. So consist of inductor, then we have bidirectional switch, so T1 and T2 is going to form the bidirectional switch because one will help to conduct in the positive, positive when the voltage is positive, the current positive, and T2 is going to help us to conduct during the current negative side. So what we are trying to do is we will be trying to change the firing angle of these thyristors, and based on that we are going to control the effective current flowing through the device. So we will be using a fixed inductor. We are not using a variable inductor. But what happens when you vary the inductance is that let's say instead of this one, we are going to use a variable inductor with the same supply voltage. So if you apply same supply voltage with variable inductor, what you are going to see is that the current flowing through the inductor is going to be different. So we are going to make this happen through this circuit. So we are going to fire this thyristor at different places, firing angles. So once you change the firing angle, you are effectively changing the current flowing through the inductor. So thereby we are trying to mimic the effect of this one. Actually, it is not the same. There would be a difference, but that's what we are trying to achieve. So here now I have drawn the circuit. So can you evaluate how you can have the full conduction, half conduction, and zero conduction within this circuit? At which firing angles you can get the full conduction, zero conduction, and partial conduction? So can you draw the voltage waveform and the current waveform during the full conduction, partial conduction, and zero conduction? So can you work out that? I will give you about 10 minutes to think of. So we have the voltage waveform, and if we provide a pulse at angle 5/2, alpha at 5/2. So this is for T1 and this is for T2. So when we are in the voltage positive mode, and then at this point the current will be 0. So what we are going to see is that the current is going to increase, but when it reaches to this point, the current will be at the maximum. So we have a positive current at this point, even though the voltage is going to negative. So since we have a positive voltage, the current will be negative. So at this point, the current is 0. We have a voltage. Since we have a voltage, we know that inductor voltage V is equals to L di by dt. So dIL over dt is going to be VL over L. So here the voltage is positive, so di by dt is positive. At the beginning, voltage is positive, so we are starting with 0 di by dt. But since the voltage is positive, the current di by dt is increasing. And when it comes to this point, the V is going to be 0. So therefore, di by dt is 0 at this point. But we have a positive voltage, positive current. Now after that, what would have, so there should be, the continuation should be there. So the current will be flowing through the device T1. Now what would happen is the voltage across the inductor is going to be negative. So therefore di by dt is going to be starting to negative. And at this point, when it comes to this is 5/2, 5, 3, 5/2, and this is 2, 5. So at this point, the current is 0, voltage is negative, therefore thyristor T1 is stop conducting. And then we provide T2 signal, the voltage is negative, and we provide a signal. So at that time, the current is 0, we have negative voltage, therefore the current is going to flow in this direction. So negative direction, current will flow. So likewise, we are going to see. So this is the current waveform when we have alpha equals 90. So at that time, we would have the full conduction. So this is the full conduction. So this is 5/2 and 3 5/2. So now if we provide the signal, not at the 5/2, but now alpha is less than 5 and greater than 5/2. So we are in between. So now what would happen is that the voltage would be 0 during this time, because this is not turned on. We only turn on at this point. So at this point, we would have certain voltage. Again, what would happen is that we would see the current flowing through the device is going to be increasing like that. Then it will become negative. The di by dt is going to be negative. So it will stop conducting at this point. And then again, it will wait till the signal comes and it will be conducting. So this would be the waveform I see with the partial angle alpha from 5/2 to 5. So within that region. So this is partial conductors. So we can have the zero conductance when you provide the signal at 5 and 2, 5. And at this point, if you consider IC, it is going to be so we are controlling the amount of current flow into the inductor. Thereby, we can control the amount of reactive power flowing through this circuit. So that's why we say thyristor control reactor. So we are controlling the current through the reactor. So thereby we can control the amount of reactive power flowing through the device. So that's how we control the reactive power to the circuit. So the time that the device conducting is known as the conduction angle. So this is sigma conduction angle. And the sigma is going to be equals to pi minus alpha times 2. And this instantaneous current we can write so during the conduction period, the current will be root 2 times cos alpha minus cos omega t over XL, and otherwise the current will be 0. So we can write the fundamental component of the current as So this is the fundamental control and current. So since we have the voltage and current relationship, we can get the equivalent susceptance of the system.
Sir, excuse me.
Yep.
Sir, should we memorize these equations in last fundamental component field current?
Yeah, you can. They are not complex equations. So this would be the susceptance. So therefore we can draw the voltage and current relationship. So depending on the firing angle, we would have different characteristic curves for the voltage. So this is if we increase the sigma, the characteristic curves are going to be shifted. The gradient will be reduced. So what we are going to see is as we for different gradients, depending on the voltage that we apply, the current that is being going through will be different. So this is for one firing angle, sigma value. For another sigma value, for different voltages, we would have the different currents going through. But when we connect this to a power system, the voltage will be in a range or similar particular around a reference value. So for the what we are going to see is that with the voltage, we are going to see this kind of a curve. So when we have the network voltage, the operating voltage around a certain voltage, then we are going to see for different sigma values, the operating point will be on this kind of a one. So this is going to be having a certain gradient. So by having the different angle and different current values, we can move in a different operating point. So that's how we are going to use the thyristor control reactor. So we can set into different operating points. So typically it will take 5 to 10 minutes. It will take half a cycle or so to respond, because we have to, if we want to make a change, we have to wait till the next firings angle. So it will take 5 to 10 minutes, quarter to half a cycle to get it response. But that will be limited again by the measurements and the control circuit that we are using. So this will tell how we can use the control the reactive power absorption to the PAX device. So this is the thyristor control reactor. So if you want to absorb the reactive power from the network, you can use this circuit. Let's say you have a lightly loaded condition in the distribution line. So we all know that when the line is in the lightly load condition, due to the capacitive effects, the line end voltage can increase. So in such a situation, we can use the thyristor control reactor. We can place that at the end of the transmission line or the distribution line. So that will be absorbing the reactive power. So whatever the reactive power provided by the capacitive elements will be absorbed by the reactor that we are going to place at the far away in the line. So this circuit will be helpful, especially in the light loading conditions where you see a voltage rise. But in the most of the cases, as we discussed in the initial section, we can see a voltage drops in the night time. So that happens because there is reactive power provided by the network, or loads will be absorbing the reactive power. Line, there is voltage drop. So if we want to increase the voltage, then we need to provide the reactive power. So we need to have some sort of circuit to provide the reactive power to the network as well. So that means we have to connect capacitors and we have to provide the reactive power to the network. But one thing we should remember is that if we take a inductor, we can control the current flowing through the inductor. But when it comes to the capacitor, we can control the voltage, but we won't be able to control the current flowing through the capacitor. So if we connect a capacitor to a system, then we are providing fixed amount of reactive power depending on the voltage. We won't be able to control the amount of reactive power from the capacitor. So when we are using capacitors, when you want to connect the capacitors to the transmission or distribution network for as compensators, we will not have the thyristor control capacitors, but what we are going to have is the thyristor switch capacitors. So either we are connecting or disconnecting the thyristor, the capacitor. So the next element that we are going to discuss is the thyristor. So if we consider the thyristor switch capacitor, it is like this. So we have this is XC, so XC is equals to omega C Vs T1 and T2. So what we are doing here is either connecting or disconnecting. This is omega t and yes. So if we consider the compensator current, so usually when we want to turn on the thyristor, what we need to consider is the current flowing through the capacitor, because we cannot control the current through the capacitor. So we have to minimize the capacitor current flow. So if this is not energized at the beginning, and if we just turn on when the voltage is at the peak, then there is a voltage drop and there will be large current flowing through. So we need to minimize the current flow. And also we have to remember that when we consider the voltage and current through the capacitor, if we have a capacitor connected like this, then we know that if the voltage is like this, then current will be like this. So the current is leading by 90 degrees. So we have to consider that as well. So if we consider the current zero, so that will be happening when the voltage is at positive peak or negative peak. So therefore what we are doing is, in operation, we will be either turning on the switches at the positive peak or the negative peak. And also we will be, if we consider the capacitor voltage, that will be placed at the, that will be remain at the positive or negative peak during the turn off. So if we assume that initially the thyristor switch capacitor is in the off state, then the voltage would be at the positive peak. So at this point, we are going to provide the firing signals. So when we provide the firing signals, the voltage is same. Now the voltage is going to follow the voltage is going to follow the supply voltage when this is connected. So we have the positive peak here. So at that time, the current will start to flow. So the So now current is zero at this point. Now when we want to turn off the thyristor switch capacitor, again we are doing when the voltage is as positive or negative peak. So let's say we are turning on at this point. So the capacitor voltage now will remain at the negative peak, and the current is going to be zero thereafter. So that's how the thyristor switch capacitor is going to operate. So if we want to turn on again, we have to wait till the voltage hit the negative, and at that point we need to turn on the thyristor. So this is how the control arrangement will be with the thyristor switch capacitor. practically, in practical circuits, we would have the capacitor. There would be the practical one usually. You have a very small inductance, and then you have the capacitor. So the functions of this small inductor is limit switching transient, dampen inrush current, and prevent resonance with the grid. So if you want to have a three-phase one, you can have the three-phase one and you can connect it in delta arrangement. And usually we would have multiple thyristor switch capacitors connected in parallel. So when you have multiple number of DSCs, so to get different reactive power injection to the network, you can either turn on one by one or you can turn in combinations, and the capacitances of the capacitors can be different. So different amount of reactive power can be supplied to the network. And also, when we depending on the network condition, we can turn on the different circuits, different capacitors. That can be explained through this. So if you have the voltage and the current, so let's say you have different capacitors C1, C2, and C3, and we can define the reference value and allowable positive delta V and negative delta V of the network. So when you're operating in a So when you're operating in a certain grid condition, S1, so you can operate at this point A with capacitor C1 operating, so you are within the limits. So if this S1 is changed to let's say S1 is changed to S2. So if you if S1 is changed to S2, now with the capacitor C1, you will be moving from A to B, but point B is outside the reference value. Now what we can do is we can move on to this point by turning on the C2 capacitor. So when you turn off C1 and if you move to capacitor C2 and turn on that one, now your operating point will move to here. So you can turn on C3 also, then your operating point will move to the point here. So in the first place, C1 and point A the with S1, we go to C1 operating point B with S1. In the third one, C2 point, I will mark this as point C with S2. So we are going to point C with S2 and capacitors C2. So thereby you can see that we can vary the operating point on the network. So that's the thyristor switch capacitor where we can control the amount of reactive power. So here we can only give step change based on the capacitors that have in the thyristor switch capacitors. But if we combine the thyristor switch capacitor and thyristor control reactor, we should be able to control the amount of reactive power fed into the network. So that kind of a system is known as the static power compensator. So I will discuss about the static power compensator in the next lecture. So with that, I will conclude the session for today. And there's a, I think Dhananjay, you have raised the hand. Do you have a question?
Yes, sir. In normal power panels, they install our capacitor banks using a power factor regulator. Then they use KVR contactors and they install capacitors. So these thyristors are already installed in those capacitor banks. So in that method, we don't use them.
No, no. In the industry we use the capacitors. So they may not have used the thyristors. Now with the thyristors we can control when it is to turn on and when to turn off. In the industry, let's say industry, I think your example is industrial plant, I guess. Or are you referring to the power system?
Industry points, sir.
Yeah, in the industrial point of view, what we want to get is the power factor improvement. So in that case, we will be couple this one continuously to the network. Am I correct? It will be
Yes,
not
sir. Through contactors.
yeah, we don't control them on and off. But here, this is going to use in a power system. So in the power system, the load will vary with the time. So we need to turn on and off. So in that sense, having a thyristor is easy. Breaker, the problem is breaker, we need manually to turn on and off, isn't it?
Yes, sir. They normally use power factor regulator
Yeah.
in the
So
predefined steps.
yeah, so that's the thing. So we have a manual switch. So here with the thyristors, we can automate it. We can sense the voltage, and accordingly we can turn on and off the thyristors, and we can connect the correct thyristor switch capacitor to the network. So there are thyristor switch capacitors operated using mechanical switches instead of the thyristors as well. So they are known as the mechanical switch operated capacitors. Did I give an answer for your question?
Yes, sir. Thank you.
So if we recap what we did today, so we looked at why we need, what are the issues that we would see in power system. Some problems occur during certain time of the day. Others will gradually come across over the years with the increase of the loads connected to a network. So what are the options that we have to regulate the voltage, whereas nighttime voltage drop, so light loading condition voltage increase, and for the gradual the load increase, and therefore inability to support the increase in loads. So what we said is that by using, if you try to install another line or transformer, that can be costly. So if we have an option that we can use where we don't need to build another transmission line or distribution line, that would be useful. So there what we discuss is that the flexible AC transmission systems will be useful, FACS devices. So we looked at the power transmission capability without compensators, how the power curve will vary. Then we looked at the what would happen if we have a shunt compensator, how the power curve will change. Then we looked at the series compensator, and we looked at how the power curve varies. So there are advantages and disadvantages going with the shunt or series compensation. After that, we looked at what are the options that we have. So we revised the thyristors, which are used with the FACS devices, its characteristics, what would happen when we give the firing angle, how the output voltage varies with the resistive load, and then we extend it to capacitors and voltages. We looked at the shunt compensation devices, thyristor control reactor and thyristor switch capacitor. So with the control reactor, we can control the amount of reactive power absorbed to the network from the network. In the thyristor switch capacitor, we can provide reactive power to the network in steps. So those two we looked at with the waveforms and control operation. So in the next class, we will look at the SVC and advanced static work compensator. Also, we will look at how we can realize the series compensation practically. Do you have any questions from the material that we covered in today's class? Okay, if there are no questions, we will wind up the lecture for today. Thank you very much for your feedback and responding to the questions. I hope that you will continue that in the next class as well. So with that, I will wind up the session. I will upload this Zoom recorded lecture to the course page in due course. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yes, sir.